purpose of this video is to go through the lecture slides for lecture 27, which compare and contrast two alternative dynamic models for econometrics. These are first of all the rational lag model, and secondly the autoregressive distributed lag model, or ARDL model for short. We'll finish by showing that the ARDL model contains many of the particular models that we've looked at during the course of this module as special cases. Let's first of all start by introducing a piece of very useful notation. That's the lag operator. The lag operator is useful because it allows us to manipulate models in order to derive the dynamic roots. So for example, if we want to write the lag value of y, we multiply by the lag operator L. So Lyt is equal to yt minus 1. And in general, L to the power kyt is equal to yt minus k. Using this notation, we can write our distributed lag model in a very convenient way. Suppose we have this expression here, yt equals beta 1 xt plus beta 2 xt minus 1, etc., plus a random error term ut. By using the lag operator, we can group together all the xt terms. We can write xt minus 1 as L xt, and xt minus 2 as L squared xt, and so on. So we get an expression of the form yt equals beta 1 plus beta 2l plus beta 3l squared plus beta 4l cubed, etc., all multiplied by xt plus ut. This expression here in L is what we refer to as the lag polynomial for obvious reasons. It's a polynomial function in the lag operator, and we can manipulate it like we can manipulate any polynomial function. It's also notationally convenient. We can write our expression now as yt equals b of L xt, where bl is our lag polynomial plus the error term ut. Now we've seen that the lag polynomial in x can be very long indeed if we've got a long adjustment period, and in fact we can have infinite distributed lag functions. However, here is where we can introduce a useful result. We can approximate any polynomial function bl, including infinite polynomials, using the ratio of two lower order polynomials. So we can reduce the number of parameters by approximating the function as a ratio of two low order polynomials. So for example, we can write bl equals cl over dl, and substitute that in, we'd have yt equals cl over dl xt plus ut, where both cl and dl are lower order polynomials than the bl function. This is what we refer to as the rational distributed lag model. Let's take a look at an example. The graph here shows a possible distributed lag function. These would be the parameters on the x variables for different lags, and you can see that it's a very long distributed lag function. However, it's possible to show that we can approximate this function by taking the ratio of two quadratic or low order polynomial functions. In fact, this is how we generated this particular polynomial function. We've taken the ratio of 0.5 plus 0.25l plus 0.25l squared over 1 minus 1.25l plus 0.5l squared. And that would give us this particular pattern of distributed lag parameters. Now let's go back to our rational distributed lag model. So if I go back one slide, if we take this formulation here, yt equals c of l over d of l xt plus ut, we can multiply through by dl, and that will give us the following expression, dlyt equals cl xt plus dl ut. So now we'll have lags on the y variable, lags on the x variable. We'll also have a polynomial function in the error term here. In particular, if we'd assume that the original error term was white noise, then this version of the model has an error process which has the same properties as the autoregressive, i.e. the lagged on y part of this process. Now, let's contrast this with an alternative dynamic model. That's the autoregressive distributed lag model. We've seen this generates what could be thought of as an ARDL model. However, if we start from the premise that the data is generated by an autoregressive distributed lag process, we get a slightly different result. Let's assume that instead we start with a model which has a mixture of lags on the x and the y variable. So we have a model, for example, here, yt equals beta 1 xt plus beta 2 xt minus 1 plus beta 3 xt minus 2 plus beta 4 yt minus 1 plus beta 5 yt minus 2 plus ut. And again, we're going to assume here that the ut are white noise errors. They're independent random noise, essentially. Now, this is actually a very useful specification because it's relatively easy to estimate, to fit to data, and many processes that we look at can be approximated by a function of this kind. We shorten it by referring to it as the ARDL model, or autoregressive distributed lag model. It differs from the rational distributed lag model because we've assumed that the error process in this equation is in itself essentially just white noise, whereas with the rational distributed lag model the error process would have some structure because of the way in which we'd entered the error term into the model. One of the useful things about the ARDL model is that it includes most of the dynamic models we've looked at already as special cases. For example, if we set beta 2, beta 3, beta 4 and beta 5 all equal to 0, we take out all the lags, we get the simple static model where we just get yt equals beta 1 xt plus ut. If we say set the parameters beta 2, beta 3 and beta 5 equal to 0, we would just have an equation which included xt and yt minus 1, and that would again be a familiar model. That would be the partial adjustment model that we've looked at in previous lectures. So this is going to be a continuing theme with the ARDL model. Essentially, it's going to be a general model which encompasses or includes within it all sorts of special cases that are of interest to us. This is potentially very useful because it means we can start from this very general framework and then we can test any restrictions which will allow us to write the model in a simpler form of the kind that we've dealt with previously. Now, let's use the L notation or the lag operator to write the ARDL model. Using the lag operator, we can write the ARDL model as dlyt, a polynomial function in L multiplied by yt, equals clxt, again a polynomial function in L multiplied by xt, plus ut, where ut we're assuming is a white noise error. For example, we can take the ARDL11 model with one lag on y and one lag on x, where we've got yt equals beta 1 xt plus beta 2 xt minus 1 plus beta 3 yt minus 1 plus the error term ut. We can write it as yt equals beta 1 plus beta 2 lxt plus beta 3 lyt plus ut. And that would be, again, potentially useful because we can manipulate this version of the model using the lag operator. We can group together the terms in y and we can then derive the distributed lag relationship with x, and in this case also with the error term ut. We should note this is not the same as the rational distributed lag model because if we group together terms, we write this as yt equals cl dl xt plus 1 over dl ut. That would give us the distributed lag form of the autoregressive distributed lag model. Then we get a moving average process, I think. We get a distributed lag function on the error term ut. So, taking the ratio of two finite polynomials in L has the effect of creating a longer distributed lag relationship between y and x. We've seen that already. However, now there will also be a moving average relationship between the y variable and the random disturbance ut. Okay, as an example of this, let's consider the ARDL11 model. that's where we've got one lag on y and one lag on x. So we can write that as 1 minus gamma L yt, that's our DL or lag polynomial function in y, equals beta 1 plus beta L xt, that's our CL function, a polynomial function in L, plus ut. We're going to assume that the u is a Gaussian white noise process, and we can divide through by 1 minus gamma L and write this as yt equals beta 1 plus beta 2L over 1 minus gamma L xt plus 1 over 1 minus gamma L ut. The relationship between the y and the disturbance term is now given by this polynomial function here, 1 over 1 minus gamma L. Now, with a little bit of manipulation, we can show that this is equal to 1 plus gamma L plus gamma squared L squared plus gamma cubed L cubed, etc., etc. This means that there is an infinite moving average process in the errors here. However, provided gamma is less than 1 in absolute value, the weights on these lagged error terms will get smaller and smaller the further we move into the past, so this will be a stable process. Okay, let's consider an example. This is an example of the sort of ARDL model we estimate very frequently in macroeconomics, where I'm relating investments to lags of GDP and lags of itself. So we've got an autoregressive distributed lag function trying to explain here the level of investment. This would be an example of an ARDL 2-1 model because, an ARDL, yes that's right, ARDL 2-1, because I've got one lag on the I and two lags on Y. In this case, investment, we can show from this equation, we've got significant coefficients on current Y, lag Y, 1 period, lag Y 2 periods, and lagged I 1 period. This gives us a difference equation of this form here. Actually, I think I got that wrong earlier. This is an ARDL 1-2 model because there's one lag on the dependent variable and two lags on the right hand side or explanatory variable. It can be a little tricky sometimes. You just have to think fairly carefully about how your notation in this context. Okay, so using this we can generate the distributed lag function of changes in the x variable on the y variable. In the long run, we can compute the long run effect by adding together the coefficients on y and then dividing by 1 minus the sum of the coefficients on the lagged I terms. So in this case, the long run effect is obtained by adding together these three coefficients on y and then divided by 1 minus the coefficient on the lagged endogenous variable here. That gives us this expression here, which works out at 1.18. That's the long run multiplier, so a 1% increase in GDP in the long run will produce an increase in investment of 1.18%, which sounds about right. Now, we can work out the distributed lag effect by using this difference equation approach here, where I write the difference equation in I as a function of current and lagged Y's and lagged I's. And then I consider the effect of a permanent increase in Y of 1 unit. Basically, this is going to show us how we approach this long run relationship that we've derived up here. If we work it through numerically, these are the results here. We get an impact effect of 1.7, then that rises in the first period afterwards to 2.23, and then it starts to decline down, and it takes a long time to approach the equilibrium. This is shown by this graph here, where we've got the red line here is the distributed lag effect of a change in Y on investment. And the blue line here is showing the long run to which the relationship is approaching. You see we get this initial impact effect, then it increases still further in the next period, then declines back down over time. Let's say a few more general words about autoregressive distributed lag models. So far we've restricted attention to fairly simple cases, but in general we can write the autoregressive distributed lag model as yt equals beta naught plus the sum of a set of coefficients on multiplied by lag y's up to p lags on y, and then a set of coefficients gamma j multiplied by lag x's up to lag q. This would be an example of an ARDL PQ model because there are P autoregressive terms or lags in Y, and there are Q distributed lag terms or lags in X. The long run effect of a sustained increase in the X variable can be calculated by taking the sum of the gamma coefficients and divided by 1 minus the sum of the beta coefficients. So we've got the sum from j equals 0 to q of gamma j divided by 1 minus the sum from I equals 1 to p of beta I. Okay, that would give us the long run effect for the general case. Again, let's take another example. This is an autoregressive distributed lag model for consumption, where we've got consumption as a function of disposable income and lagged values of consumption. In this case we've got one lag of disposable income and we've got two lags of consumption. So this would be an ARDL 2-1 model. Again, once we've estimated the model, we can calculate the long run effect by taking the sum of the coefficients on disposable income, so that's the sum of these two coefficients here, and divided by 1 minus the sum of the coefficients on the lagged values of consumption. That gives us this expression here, and this works out at 1.009. Again, what this is telling us is that we've got a long run income elasticity of consumption that's very, very close to 1, which seems reasonably sensible from an economic theory point of view. One key thing to note here is that if the sum of the coefficients on the lagged endogenous variables is equal to 1, then we cannot calculate the long run effect of x on y. It's not defined. This is because if we take the sum from I equals 1 to p of beta I, that's equal to 1, this would imply 1 minus that sum equals 0, and we need to divide by this expression, and division by 0 is not possible. So this is only defined when the sum of the coefficients on the lag values of the endogenous variable is not equal to 1. If this is the case, if we do get the sum of the coefficients equal to 1, then this indicates that we should be different in the data before we estimate the model. Now, we said at the start that one of the advantages of the ARDL model is that many of the special cases that we've considered so far, many of the models that we've been discussing on this module, are in fact embedded within or encompassed by this framework. They're special cases. And that's useful because it means that we can start with this general case and then we can test any restrictions that are necessary to get us to these particular models. So for example, let's take the ARDL 1-1 model. That's a model in which we've got one lag on X and one lag on Y. We write it in this form here. There are a number of models that we've looked at on the course that are special cases of this. For example, the static regression model is obtained by setting beta 3 and beta 4 being equal to 0. That would give us yt equals beta 1 plus beta 2 xt plus ut. Very familiar static regression model. So we could start by estimating this model and test the restrictions necessary to get us to this model. Secondly, if we were to impose the restriction beta 3 equals 0, we'd have an equation of the form yt equals beta 1 plus beta 2 xt plus beta 4 yt minus 1 plus ut, and that is the partial adjustment model that we discussed in the lectures last week. Another model that we've talked about quite a bit is a model in first differences. Well, if we impose the restriction beta 3 equals minus beta 2 and the restriction beta 4 is equal to 1, then effectively that would mean that this general equation here could be written in the form delta yt equals beta 1 plus beta 2 delta xt plus ut. In other words, a model in first differences. Now, again, we could in principle test these restrictions, Well, this is actually quite a tricky test, because if the null hypothesis was beta 4 equals 1, then the test statistics wouldn't have the standard distribution. But that's something we can talk about at a later date. Finally, another model that we've talked about quite a bit and quite a few of you have used in your projects is the autoregressive error model. And again, this can be seen as a restricted version of this model here. If we impose the restriction beta 3 equals minus beta 2 beta 4, then we can combine, or we can write this model as yt equals beta 1 plus beta 2 xt plus vt, where vt is equal to beta 4 vt minus 1 plus ut. Okay. If you're not happy with that, try imposing this restriction, substituting into this expression here and rearranging. You'll find that this drops out quite neatly. So again, the autoregressive model is one, or autoregressive error model is one in which we can view it as a special case of the model here. The tricky bit here is that the restriction that gets us to the AR1 error model is a nonlinear restriction in the parameters. And nonlinear restrictions are quite tricky to test for. Again, it creates problems for the testing procedure. Okay, that's it for my lecture slides for lecture 27. Okay, hope you find that useful. There are some lectures are available if you wish to use them, but that's as much as I'm doing today.